We are going to look at method 3, but before doing so, we will first show a general result. If we consider a function f, which is a function of x, x dot, and t, so t here is our independent variable, and x is a function of t, and x dot is dx dt, then the differential of f is written as this. So in other words, since f depends on x, x dot, and t, any change in f gets contributions from all three of these derivatives. If we go now from this differential to the total derivative, df over dt, well, we can just divide both sides by dt. And now we notice a few things. Okay, dx over dt is x dot, dx dot over dt is x double dot, and dt over dt is 1. Now we are going to impose two conditions on f. The first condition is that partial f partial t is 0. That is, that there is no explicit dependence on time, only implicit dependencies through x and x dot. So in other words, x and x dot can be functions of time, and because those might change with time, f can change with time, but f does not directly depend on time. The second condition is that f will satisfy the Euler-Lagrange equation, which with our current set of dependent and independent variables will look like this. Going back to this equation, we first apply condition 1, which eliminates this term and leaves us with this. Then, using condition 2, that f satisfies the Euler-Lagrange equation, we can replace partial f partial x with d by dt of partial f over partial x dot. Now, looking at these two terms, we notice a sort of similarity. Here we have partial f partial x dot, and here we have the time derivative of partial f partial x dot. Here we have x dot, and here we have the time derivative of x dot. If we recognize this pattern, then we realize that this is just the result of a product rule. And so we can combine both these terms into the time derivative of partial f partial x dot times x dot. Notice that on both sides of this equation, we have a total derivative with respect to time. So we can pull them both to the same side and rewrite our equation like so. But again, when is the derivative of something 0? Well, it's when the thing inside is a constant. So we call this expression partial f partial x dot times x dot minus f a constant e. In this case, it would be a constant with respect to time. The reason why we're calling it e is because when we go on to the Lagrangian and Hamiltonian case, this constant e will play the role of energy. But even if we're not dealing with time and Lagrangians and so on, as long as the two conditions we mentioned are satisfied, this will be a constant quantity. So the result is, if we are searching for an x of t such that this integral is stationary, and the other condition that partial f partial t equaling 0 is satisfied, then this expression is a conserved quantity or a constant, where in this case t is the independent variable. Now we are ready for method 3. Again, we are trying to minimize the integral, which gives us the area. We again pull out dx and write the remaining part in terms of y prime. And so this is our f, where x is the independent variable and y is the dependent variable. But we notice that partial f partial x is 0. And so we can apply the result that we got previously. And so remember that the condition we need to apply that result is that the partial derivative of f with respect to the independent variable should be 0. That is indeed the case over here. So translating that to our current situation, that tells us that partial f partial y prime times y prime minus f will be a constant. So we evaluate that. All right, we get this expression. We notice some common factors of 2 pi y. We can, in fact, pull out 2 pi y over square root of 1 plus y prime squared. And then other terms look like this. We see that the y prime squared is going to cancel. You'll have a minus 1 left over. So this gives us this simplified result. Rearranging and absorbing some constants all into a single new constant and solving for y prime, we end up with this result, which we can integrate. And in fact, this is pretty much identical to one of the equations we had in the previous methods. And so we get pretty much the same result. So once again, this is much easier than method one. And the thing to look out for here is, does your f depend explicitly on the independent variable or not?